Oh, well, it's you again. You're coming back for more. All right, so let's talk about Unit 10.4. We're going to finish off Chapter 10 today. So, we're going to talk now about which factor? Well, if you know how to read, temperature. Now, I have an example here to illustrate this factor. I have a bunch of cookies that I would put on a cookie sheet in the middle of the summer on my dashboard in my car. And I have a bunch of cookies that I would put typically in the oven. Now the question is, which ones will cook faster? The ones that are in my car and it's 35 degrees outside and the sun is beaming into the car, or the ones that are in the oven? Excellent question. Now, if you're a smart cookie, you're going to answer this one here. Why? Because the temperature is higher than over here. Yeah, it may be warm in my car, but you can well imagine it's not 350 Fahrenheit. Otherwise, if you sat in the car, you'd be cooking yourself, which is never the case. As hot as it may be in the summer, you may be sweating, but you're not literally cooking. So these are going to take longer to bake. These will bake much faster because the temperature is higher. So if we compare or talk about the collision theory, we're going to say that the higher the temperature, the more kinetic energy the particles have. If they have more kinetic energy, they will collide more, which will mean a faster rate of reaction. Now, that was it for temperature. Pretty obvious, pretty easy. The last point, catalysts. What are those? So catalysts are substances that will speed up the rate of a reaction, but what they'll do is that they'll affect the activation energy. So examples of those, because some of you may say, well, what's a catalyst? The most obvious would be enzymes in digestion. So you have substances in your, for example, gastric juices or intestinal juices that will help digest substances, the substances that you eat. If those enzymes weren't there, the digestion process would take much longer. So those enzymes speed up the whole process. Now we're going to take a look at how. I kind of said that they affect the activation energy, but let's take a look at that. Okay, so we have two reactions here, the blue and the red. So the blue one is the regular one, what we call the non-catalyzed reaction. So this is the regular one, no extra substances involved, than the normal reactants. Now over here we added a catalyst. So that catalyst, what does it do? It creates what we call an alternate pathway, so a different type of reaction with a smaller activation energy. Obviously, if the activation energy is lower, it's much easier for the reactants to get over that hill and thus react, which speeds up the rate of the reaction. Now, one thing that you have to know, a catalyst is never used up. It's kind of a facilitator, so it doesn't react per se. Whatever the substance, the catalyst is at the beginning of the reaction, it remains whole, it doesn't change, and so you'll have the same substance at the end. It doesn't get consumed nor transformed. How does this translate in terms of numbers of particles that react? So here you have a Maxwell-Boltzmann distribution graph. We saw that a few lessons ago. This is basically a graph that shows you the number of particles present in a reaction versus their energy or their speed, which are two items that are basically related, because remember that the kinetic energy is equal to half the mass times the velocity of a particle. So velocity plays a factor into energy. That's why they're kind of interchangeable in this graph. Now, if we put values over here on this graph, just for better understanding, we have 1,000 kilojoules, let's say 2,000, 3,000, 4,000, 5, 6, and so on and so forth. So here we have 5,000, and here we'll have 3,000 kilojoules. So the regular graph, the non-catalyzed reaction, so the one that doesn't have a catalyst has a specific activation energy. This line, if you remember, represents the activation energy of 5,000 kilojoules. So all the particles that have at least 5,000 kilojoules will be able to react. The others on this side, those are all the particles, all these here, if you look at your curve, all these are the particles that don't have 5,000 kilojoules. These would not react. They would have elastic collisions. These over here would have inelastic collisions, because they have enough energy, they'll collide, they'll break apart, they'll become products. Now, if I add a catalyst, we said before that when we add a catalyst, it's lowering the activation energy of the reaction. So how do we show this on this type of graph? Well, we basically move this line over to the left towards a smaller value of energy. So now the catalyzed reaction may have 3,000 kilojoules as a threshold. So anything that has 3,000 kilojoules or more, so all these particles over here will be able to react, and those on the left will not be able to react. So as you can see, there are many more particles that are allowed or can react because the threshold, the activation energy, is much lower. And that's why we say that when we add a catalyst, because the catalyst lowers the activation energy, more particles can react, and it speeds up the reaction. It increases the speed of a reaction. Now, what's an inhibitor? It's the opposite. It's a negative catalyst. So what will it do? It will increase or raise the activation energy. So if I illustrate it here, I would have the following graph instead. So I'd have something that looks like this. And as you notice, I'm not changing the height of the line for the products nor the reactants. They always have the same value of potential energy. The only thing that changes is really how high the hill is that they have to overcome in order to become products. So I'm increasing the value of the activation energy, making it more difficult for particles to react, which means less particles will be able to react because I just increased the value of the activation energy. So if we looked at the Maxwell-Boltzmann graph over here, how would that look? Well, what I'm doing now is moving this line over this way towards a higher value for the activation energy. So now, for example, my particles would need 6,000 kilojoules in order to react rather than 5. So I have even less particles, only these are able to react. All these over here don't have sufficient energy to react. So it's going to give me a much slower reaction. Okay, so again, we call this an inhibitor or a negative catalyst. Why do we use those, or how do we use those? For example, to increase the shelf life of food. So when you have a preservative in a food, that's what it does. It basically slows down the decay of the food. It slows down that chemical reaction that makes the food rot. So an inhibitor in this case is very practical, it's very useful. Same thing for medication. We want whatever the pharmaceutical companies want their pills to last long enough. If you buy Tylenol, you don't want to have to throw the bottle the next week because you didn't take them. You want the medication to last a certain while. So they'll put chemicals in there that will slow down the decay of the actual pills so that they remain efficient for a while. So that's what we use inhibitors for. Now, what type of catalysts are there? Some are called homogeneous. Basically, they're found in the same state or phase as the reactants. Remember, we talked about gases or aqueous solutions, mostly is what we're going to encounter. So because they're in the same state or phase, they're going to be much more efficient. So it creates a reaction. In this case, the way it works, yes, it lowers the activation energy, but how does it do it? It creates intermediates. If you remember, an intermediate is a substance that's created during one step and reused in another step. So it creates a mechanism basically. So you have at least 2 steps in your newer reaction. So you start with a reaction that has 1 step, but it becomes a mechanism with a minimum of 2 steps. So how does this translate into a graph? Well, my original reaction had 1 step, so 1 activation energy. In this case, because it's broken down into 2 different processes, I have 2 hills to my process, 2 parts, but with each a smaller activation energy. So this is much easier to overcome, these two, than to have to go all the way up the hill over here. So it helps the reactants react. It speeds up the reaction in that way. Another type of catalyst that you can encounter is a heterogeneous catalyst. In this case, we're going to have a solid. Very often it's going to be a type of metal. So you have it here. And what does it do? Well, it basically weakens bonds between substances. So you're going to have the reactants here that will kind of latch onto the catalyst. So this would be your catalyst over here. And that weakens their bonds. And because their bonds are weaker, we don't need to supply as much energy to break them, which essentially lowers the activation energy and facilitates the reaction and therefore increases its rate. An example as to where we use that, production of fertilizers or explosives, because if you don't know, many chemicals are used, or similar chemicals are used in both. That's why they're used for both. And the last example, last type of catalyst, would be a biological one. We were talking about enzymes before and digestion. Well, that's where you would encounter biological catalysts. So those enzymes are big protein molecules, and they will facilitate your digestion. Now, digestion normally would be an extremely slow process that would happen at very high temperatures, but since we're not walking balls of fire, there has to be something that kind of helps around the way. Otherwise, we would be walking balls of fire. So those enzymes facilitate the digestion and make it happen at a lower temperature. And what does it do? There's two types actually of enzymes. You have the lock and key model. So you have an enzyme that will basically latch on to something that you're trying to digest called a substrate. And if the shape fits the enzyme, if the shape of the food or the molecule fits in the enzyme, that enzyme will break it apart, or in other words, digest it. So you see here the food, or the food is in a particular shape. It latches onto the enzyme. We call, by the way, the part where it latches on the active site. So it's only a very small part of the enzyme that actually does the job. So that enzyme breaks this molecule apart into two parts, which are easier to absorb by your system. And we call these at this point nutrients. So that's the first model, the lock and key. So again, what is digested only fits onto certain types of enzymes. As you can see, it has to fit, the shape has to fit. And the next one is the induced fit model. If you look at the food or the shape, it doesn't fit into here, but this works more like a piece of clay. So the enzyme, the shape of the enzyme will adapt, so to speak, to the food that has to be digested, as seen in here. And it will do the same job. It will then separate or break apart the molecule into smaller pieces called nutrients that can again be absorbed more easily by your body. So that's a third type of catalyst. Now, what you have to remember from this lesson, a couple of things. A catalyst always lowers the activation energy, which means that the reaction would occur faster because the hill becomes lower, which also implies that more particles can react because the activation energy is lower. And you have to understand the difference between the different types of catalyst. A homogeneous catalyst will create a mechanism, so you'll have several steps to your new reaction. A heterogeneous catalyst will weaken bonds, and this one was just thrown in as general knowledge. So that's it for chapter 10. You just saw the last lesson of that chapter. Hope it was clear. Once again, if you have questions, see me in class. Bye.